We're carrying out these trials in order to come up with practical repair techniques in areas where homes are more vulnerable to liquefaction.
The first method, the rapid impact compaction, works by taking a large weight and dropping that and creating a crater in the ground. What's happening below the ground is that ground is becoming denser. As that material becomes denser and stronger and stiffer, it takes more and more energy before the ground will liquefy. The rammed aggregate pier method is where gravel is inserted below the ground in vertical columns, and it's put into the ground by high frequency vibration and force. As those gravels are pushed into the ground, the material that's in the ground is displacing and being squashed together and becoming denser. Underneath the existing homes, the method that can be applied is the horizontal soil mixing. Now, this method itself works by drilling horizontally underneath the home, popping out on the other side, attaching a mixing blade, and then pulling that back through, rotating that in the ground, and as that's rotating through, adding cement and mixing that into the ground. As that cement is mixed into the ground, you leave behind a column of mixed soil and cement that hardens to form like a weak rock material, which doesn't liquefy. And then many of these beams can be constructed in a horizontal layer underneath the home, and the testing has shown that the soil in between these beams is now confined and is not going to liquefy either, giving us some very exciting options that can be applied underneath homes that are repairable. The second phase of testing has been to simulate the effects of an earthquake.
We brought a big machine down here, one of our largest. It's called T-Rex. It allows us to shake the earth for various purposes, and for this project we are trying to shake the earth and generate a downgoing shear wave that loads the soil just like an earthquake would, so we can see how it will perform during earthquake shaking.
There have been a lot of instruments installed in the ground, both in the ground improvements and below the ground improvements, and then we've looked at how the ground has been responding and at which point, at what levels of shaking have been required before those layers would liquefy. And what we have seen with these ground improvements is that we need very high levels of shaking before those layers will liquefy, compared to the layers beneath or the natural unimproved ground, which readily liquefies at more moderate levels of shaking.